leave it open. See? 30 people out there waiting. All right. Any questions from last time? Homework? Huh? Somebody say something? No? All right.
You sent out a cleanup proof?
Cleanup proof. Send out a cleanup proof. Yeah, I can do that. I have a sketch. And yeah, I can do that. Send me an email to remind me, otherwise I'm bound to forget. But by the time I make it back to my office, it's very much the same idea. Let's see, GVT. Actually, it's the same, but maybe seeing it in a more condensed form will be helpful. All right. Okay. So where did we leave off? We left off. I described an algorithm for shortest path trees. So just high-level summary. First algorithm for so high-level summary. Okay, we had an algorithm for MST, which was choose smallest edges, smallest weight edges, weights that don't form cycles. Right? You do that, that builds a minimum spanning tree. Algorithm 2 for minimum spanning tree was build a tree, or I should say grow a tree, connecting edges to the tree, connecting minimum weight edges, to tree being grown, that don't form cycles. Right, so the only difference between those two algorithms was the first one just picking the minimum weight edges, whether or not they're connected to one another. The second one, you're sort of growing out this tree connecting these minimum weight edges. Okay, and the algorithm for the shortest path tree that we saw. Which is called Dijkstra's algorithm. Okay, again, you're growing this tree. Connecting nodes. Always from a root A. So grow a tree rooted at A. Okay, connecting nodes. Whose connected path would be the next closest. Okay, so if you remember the last algorithm we looked at, you have this tree that you're building, and the next node that you're going to add to that tree, or the next edge that you're going to add to that tree, is the next closest node slash edge. Right? You're always choosing the minimum distance. Right? We're choosing some node that minimizes something, and that thing that we're minimizing is essentially the distance of that node to that tree. Okay? So we're gonna look at this again, and we're also going to do another version called Bellman-Ford or distance vector. It has two different names in two communities. I guess Bellman-Ford is the algorithm, and distance vector is the implementation of the algorithm in. Okay, but first, let's look at why these shortest path algorithms work. So it's interesting. Shortest paths are very, very useful in real life, right? You want to figure out how to walk somewhere. You want to take the shortest path. Yet no one formulated an algorithm on this problem until the 1950s, when Edgar Dijkstra formulated this thing. Okay, and he's, in some sense, the father of algorithms because he did that, or a father of algorithms. I guess there were some other guys before. He was a real character. He passed away only recently. In fact, I gave a talk at University of Texas. I spoke in front of him, and he's a real stickler for when you give a talk and you have slides and you use colors. Don't use colors excessively, and why'd you make some nodes blue and some nodes red? Actually, my talk, it was blue packets and red packets, and he wondered why I was making some blue and some red. Anyway, let's not get too far off the subject today. He was just a really interesting guy, and I mean, this is a seminal contribution that he made to these algorithms. Okay, so what can we say about a shortest path? So consider a shortest path in a graph. Okay, let's say N1, N2. Let's not use N. A1, A2 sub K is the shortest path from A1 to AK. Now I'm going to make some claims. I shouldn't say E. There can be more than one shortest path. Let's say A shortest path. Okay? Shortest, I mean minimum. When you're adding up the weights of the edges along the path, that's the length of the path. So shortest path is the path of minimum weight. Okay, so my claim. A1, A2, dot, A sub K minus 1 is a shortest path from A1 to AK minus 1, and A2, AK is the shortest path from A2 to AK. Okay, how do you prove this? So I'm telling you that A1 to AK is a shortest path from A1 to AK. And now I've got this subpath, A1 to AK minus 1, following the same route. How do I know that that's the shortest path as well? How do I prove that? Faisal.
Well, for A1 to AK minus 1, you're going to choose the minimum weights of each link. So that means that A2 to AK minus 1 has to be minimum weights as well. And then to K, if you choose a link from AK minus 1 to AK, there has to be minimum weight too.
I think you're reversing the logic. So, Ron.
What are your subscripts at the end of the two claims?
Oh, this is A1 to AK.
This is A1 to AK minus 1. This is A2 to AK. So this path has the first node kicked off. This path has the last node kicked off. David.
Because if it wasn't, then you could just take that short path to AK minus 1 and then take 2.
Yeah. Here's my path from A1 to AK. I've told you it's the shortest path. Right? And the claim is that this path here, from A1 to AK minus 1, is also the shortest path. From A1 to AK minus 1. It's the shortest path from A1 to AK minus 1. Suppose it wasn't. Okay? So let's say this path has length L. Suppose there's a shorter path from A1 to AK minus 1 of length L prime. Okay? Well, the length path here from A1 to AK is going to be L plus the weight of edge AK minus 1 AK, right? But there's this other path. with weight L prime plus the weight of AK minus 1 AK. And if L prime is less than L, then this other path is short. All right, it's a contradiction. So this is proof by contradiction. Okay? Everybody understand the picture? And I'm saying this, we're assuming that this is the shortest path from A1, or a shortest path from A1 to AK. And my claim is that the path from A1 to AK minus 1, following the same set of nodes, is the shortest path. And the proof is, suppose it's not. Suppose there's a short path from A1 to AK minus 1. Well then, you follow this shorter path to get from A1 to AK minus 1, and then take the next step to AK. That necessarily has to be shorter than this path that we have here. So that can't happen. It's a contradiction. Okay? Who understands? All right. And the proof for this is exactly the same, right? Except instead the picture looks like this. I've got A1 to AK. Here's A2, right? And I'm going to call this L. And there's some other path that's supposed to be shorter, L prime going like that. And it's the same argument, right? Okay, and so let's revisit the oh, and another thing about Dijkstra. For years I was misspelling his name. I finally realized it's IJK. D-I-J-K. Will never misspell it again in my life. All right. I had this shop teacher in high school. Comes in the first day, he says, "My name is Mr. Seiler." S-E-I-L-E-R. If you spell it backwards, it's relies. All right? You remember that, you get an A. That's what the guy said. And I got an A. And I wasn't very good at shop. You can imagine someone who can't even write straight on the board, right? I mean, okay. In fact, I got made fun of in college because I built a computer stand from out of wood for a computer that I had, and I built a keyboard stand for it, which I thought was genius. I took a flat piece of wood and just nailed it like into the table, and it swiveled and everything. But you couldn't put anything heavy on it, heavier than a keyboard, because it would just break right off, right? So I wrote on it, "Do not sit here." And all my friends thought it was pathetic. Like, what a pathetic. They didn't appreciate the swivel. Well, anyway, okay. So getting back to Dijkstra's algorithm. All right. So remember, Dijkstra's algorithm was you're growing a tree by connecting the nodes closest that hasn't already been connected. Right? Do people remember the algorithm from last time at the end of class? I presented formally where you got this set of nodes and the set of edges, and you have the set of nodes already added, and then you consider the set of nodes that have not yet been added to the tree, but that are neighbors of nodes that have been added to the tree, and then you figure out their minimum distance, the distance including their neighbor plus the neighbor that's been added has some distance to the root that we've already determined. We already know that shortest path distance. We have a set of nodes who'd be added next. We take the minimum one and add that next. Okay, so I want to make a claim about Dijkstra's algorithm. Nodes are added to the tree in non-decreasing distance order, meaning every time I add another node, it's no closer than a node that was added previously. But if you look at this D of the node that we keep adding, it doesn't necessarily grow every time. It might stay the same as the previous node, but it never shrinks. Okay? How do we prove that claim? How have we been proving everything in this class? Yeah, contradiction. Sometimes we'll use induction, but sometimes a contradiction is usually easier. Okay, so I'm going to prove by contradiction by saying, assume some node is added distance to root less than some previous node added. Okay, and obviously, if this happens, it happens first for some node. So let A be the first node for which this happens. Okay, so let me try and draw a picture. I always wanted to do a similar thing, but my name backwards is Needs Never, so it doesn't really help you remember it. In fact, I don't even pronounce my name correctly. It's supposedly supposed to be Rubenstein, but my dad told me it was Rubenstein, so that's what we go by in the Rubenstein house. Okay, where were we? Yeah, the picture. Okay, so there's some node A. Okay, we've got the root of our tree, and we've been building this thing up, the shortest path tree. And at some point, we connect A, right? And we had already added some other node B that was further away. Okay, so the distance from root to A is less than the distance from root to B. Okay? And so let me say one more thing about B. And let B be a node closest to root whose distance is greater than A, but has already been added. Okay? So when we add A, there's a bunch of nodes that may have already been added that were further away from A. Let B be the closest of those such nodes. All right? So B is attached to some node C, and C is closer than A. Okay, and A is affixed to some node, let's call it M. Okay? Now if you think about the algorithm, why would we add B before adding A? Well, if we added B before A, that would mean that M could not yet have been added. Because once M was added, right, and we added it according to its shortest distance, then in the next step, we'd be considering adding A along this edge. We we would add it before adding B. M. People follow? Again, the rule is when you're considering whether or not you should add a node, you take every node that's attached to the node that's already been added, and you take the weight of the edge and also the weight of the path to that node. The weight of M has some. M we've already computed some distance if it's already been added. It has some distance, and now we're going to say the distance from M plus this edge is that smaller than any other node we could possibly be adding. And clearly that would be smaller than B because in the end it's small. It's not like the edge weights are changing. So the only way we wouldn't consider that by the time we're adding B is if we have not yet added M. Okay? So that implies that when adding B, when we added B, we did not yet add M. Else would have added A before B because it's closer. But clearly if A is closer to the root than B, then M is closer to the root than B, right? Okay, and M is no further than A from root. Okay, so if M is closer than A, then that's already a contradiction because A is supposed to be the furthest node, right? That was added before, that was added out of order. Right? We said let A be the first node for which this happens, that it's added out of order. Or I shouldn't say the first node, I should have said the closest. Okay? And if two nodes are tied, use fewer hops. Hops is the number of edges. People familiar with that term? And the number of hops is the number of edges you have to take, where you're not concerned about the distance. So I should clarify that. Hops equals number of edges taken. Okay, so the idea is this. A is the closest node that was added out of order, meaning that some node that was further away was added to the tree before A. And then we showed that if it's the closest node that's been added out of order, then M couldn't have been added yet when we added B. So then M was also added out of order. But the way we chose A, M also satisfies this property. So A couldn't have been the closest node / minimum number of hops. That's M. So that's a contradiction. It has fewer hops. People follow the contradiction? Who gets the contradiction? Who doesn't get it? Okay. It all has to do with the way that I'm picking A. So the claim is that you're adding these nodes in increasing order of the path, the length of the path that connects them to the root. Okay? So suppose that claim is false. Then I find a node A that's been added after some node B where A is closer than B. Right? That's just stating the opposite of the claim, and we're going to prove that that cannot happen. Okay, so I'm going to be a little bit smarter about how I choose A. I'll say let A be the closest such node, where if two nodes are the same distance. So for instance, if this edge has length 0 M and A are going to be the same distance from the root, choose the one with the fewest number of hops. Okay, the fewest number of edges that you take. That way, if A and M both satisfy this property, I would choose M. Because they're the same distance, but M has fewer hops to the root. Okay? So now, I've chosen this A. It's the closest node that's been added out of order. Okay? Now let's look at why it got added out of order. When we chose to add B, all right, so this is an edge. When we chose to connect B to C, okay, what we did was we compared all the nodes that have not yet been added, right, to connect to other nodes that have been added. And the distance that we're going to use is the distance of this path for A would be the distance of this path plus this edge. Well, once we've added M, we start doing this. Before we've added M, we're not doing that comparison yet. Okay? And so when we're adding B, if M had already been added, and we were doing this comparison such that we're checking to see whether A attached to M has the minimum distance, well, it would have a distance less than B to the root. The only way we add B first is if M has not yet been attached to the tree. Okay? If M has not yet been attached to the tree, then M is the closest node that gets attached after B. M is the closest node that's out of order. It wasn't A, and that's our contradiction. Okay, I said choose a node that satisfies this property. And I said, well, if this thing happens, then this isn't the node that satisfies the property. This is the node that satisfies the property. And that's a contradiction. Okay? Nodes are added in non-decreasing order. Okay, now let's prove Dijkstra's algorithm finds the shortest path. Okay, this we're going to prove by induction. Okay, so first the base case. First node add. Okay, well, what does the picture look like? We've got the root node that's already added to the tree. And there's a couple of other nodes that are directly connected to the root node. Right? And then there's a bunch of nodes that aren't connected to the root node. So what does the algorithm do? The algorithm says, consider all nodes that are connected directly to the root. Connected directly to nodes that have already been added to the tree. So the root's the only node that's been added to the tree in the beginning, right? And choose the one that minimizes the distance from the root to the node that you're considering that's already been attached, plus that additional edge. So here we're only considering the root, which has distance 0 to itself, plus these edges. So we're going to basically add the minimum weight edge. Right? So if this is 2 and this is 5 and this is 7, we're going to add this guy first. Okay? That's pretty obvious. Nobody can be closer to the root than this guy. Right? There's no way you could get a path of length 1.9 when all edges are 0 or positive. Right? Because anybody who's closer is going to have to go through one of these nodes, and already you've traveled distance at least 2. So nobody else can be closer. Right? So for the first node added, it holds. The direct connection to the closest along the shortest edge is the shortest path. Okay? Now suppose we're going to do the inductive step. Suppose the claim holds nodes for all I less than n. When adding the ith node. Okay, so it holds for the first. Now assuming it holds for the first node, second node, third node added, up to the n minus first. Okay. Show also holds for the nth node. So what am I saying now? Now we're looking at some point later on where I've already attached a bunch of nodes, and I'm saying suppose this is the node that I'm attaching next. So this is the nth node to be attached. Okay, how do I know that this is going to be its shortest path? Am I setting up? Let me just think. Maybe I'm setting up this induction wrong. Okay. Well, let me just a little bit fuzzy here. So let me strengthen statement. We're going to actually prove the ith node added is the ith closest node. Okay? So that holds for the base case, right? First node we add is the closest. And suppose the claim holds all I less than n when adding the ith node. So what I'm saying is all these nodes that have been added, we have added, so we've added all n minus 1 closer nodes. Right, by the inductive assumption. Okay, and this is the nth closest node that we're adding now. Right? And the point is, when you add this, what does the shortest path node for this node look like? The shortest path of this node, it's going to attach to some other node. Okay, the other node it attached to has to be closer, or as close, right? And we know from an earlier claim that the path from the root to that node has to be its shortest path, which we've already added, right? So this is the shortest path to this node to which nth node will attach. Right, so the point is the shortest path going to the nth node is actually already present there. The shortest path to our nth node consists of the shortest path to its previous neighbor plus an additional edge. And that's already there. So that path will be considered at this point. So in the nth iteration, the shortest path to the nth node will be considered. Okay, no other nodes by the inductive assumption no unattached nodes are closer. Hence, not considering those paths is not problematic. For attaching in. I mean, no other nodes can be closer, so by considering these other nodes, none of them can have a smaller distance than the n we're considering, and we are considering n in this nth node in this nth iteration because we do have the shortest path to the neighbor to which it's going to attach. So it will be attached next. Okay, that's proof of Dijkstra's algorithm, proof of correctness. So again, the way Dijkstra's algorithm works is in the nth iteration, you're considering a bunch of nodes, and the node that's going to be attached is the node who has the you check all other nodes it can attach to that are already part of the tree, and you choose the node, or you choose the edge that minimizes the length of the path to the node that's already been attached, plus the node being attached. Okay, and the point is that when we get to the nth node, its predecessor must have already been attached because all nodes that are closer have already been attached by the inductive assumption. Okay? Who gets it? 1. All right, 2. Let me try and explain it this way. Who understands how to run the algorithm? I mean, if you don't understand the algorithm, you understand the proof. So who gets the algorithm? Okay, most of you get the algorithm. So all we're saying is this. Here's the node I want to attach in the nth iteration. Okay? I always attach the closest node. And my claim is that there's a bunch of nodes that are closer. They've already been attached. And the nodes that have not yet been attached are some that might be the same distance and some that might be further away. Okay, and I just want to show that Dijkstra's algorithm can now attach this node that's one of the closest. And the point is, I'm trying to decide whether or not to attach this node. It's possible if its shortest path connects via an edge to a node that's already been attached. That has to be the case. All these closer nodes have already been attached, right? So this check will be done on the next iteration. I will check to see. I will check this path. I will compute this distance. And this node, because I'm computing this distance, and this is the minimum over all possible distances for all these other nodes that are further, the distance to these nodes cannot be less than this distance that I'm computing now in this nth iteration. So I'm checking this distance, so I'm going to add this node next. That's the basic idea. Okay, so that's Dijkstra's algorithm. So just to recap, Dijkstra's algorithm, you're extending the ends of the trees. Okay, a problem with Dijkstra's algorithm and the minimum spanning tree algorithms is that they were centralized. Which means you needed a global view of the network in order to compute them. Or a global view of the graph. Okay, and we're also interested in networks where what's going to happen is, I guess now's a good time as any to explain how all this stuff relates to networks. Okay. When you type in, if you use the web, all right, and you type in www.newyorktimes.com. Okay, this gets translated into a number. It's called an IP address. We're not gonna worry about how that's done right now. If you take the computer science network course, you'll know that this is done via a mechanism called DNS. But it gets translated into an IP address, which is the form. If you've seen something like this, it'll be like 118.47.12.16. Okay, so for our purposes, it's just an identifier. And now, here's your computer. Okay, and you're attached to this network, right? You plug in this Ethernet cable, this thing that looks like a big phone jack, right? And that connects you to the wall, and that actually connects you to a switch, which eventually connects you to a router. Okay, so this thing is a router. Okay, and inside the middle of the network are lots and lots of routers, which are essentially the nodes of the graph. Okay, and NewYorkTimes.com, some big server, or no, I guess we have the IP. 16. Okay, and when you make that request and your packet that you're sending into the network has this ID on it, it's got to get routed to the right place. Okay, and every router has to decide, how do I get to this location? If I get a packet with this ID, how do I get to that location? So the way you can think about doing that is you're going to take this as your root of tree, and you're going to build the shortest path tree. Okay, so here's the network. Okay, you're going to build the shortest path tree rooted at this node over here. Okay, so now if this guy wants to send a packet here, there's a unique path to do it, and every router knows how to get there. Okay, and you build the shortest path tree, so it's the shortest distance to get it. The problem with the way I just did things was I had this global centralized view. I could look at all the nodes at once and say, how do I want to build this path? Or I could run Dijkstra's algorithm. I could basically start extending the tree from that point. But in the real network, a lot of the time, you don't have this centralized overview. Every router only knows what's happening around it. Can't see the big picture. Okay, it doesn't know, hey, I'm the next one to be added because I'm the next closest. I mean, who's closest? That information isn't being passed around. Okay, so what we want is a distributed algorithm. Okay, so each node is to keep some local, some minimal state. Okay, and that's what leads us to the Bellman-Ford algorithm. Bellman-Ford is a distributed algorithm. And you're going to see the way I describe it is somewhat different. When we describe the centralized algorithm, there was this one entity, me, the oracle, or you, who made all the decisions, right? The algorithm said, take this set, put these nodes in this set, take the one that's smallest, move it from this set to that set, right? In a distributed algorithm, every node is going to be doing its own function. And nodes pass communications, neighboring nodes. So by neighboring, I mean connected by an edge. Pass info. Okay, so here's how Bellman-Ford is going to work. Okay, Bellman-Ford tree, Bellman-Ford building a tree. Rooted at R. Okay. Each node remembers its shortest currently known distance to R. And the neighbor it takes to get there, to get to R. Okay? When it receives an update, so a message from a neighbor, about that neighbor's distance to R. If that changes its shortest distance, when a node n receives an update message from a neighbor about that neighbor's distance to R, if n's minimum distance to R changes, it updates its state, n updates its state, updates this distance, and informs its neighbors. The algorithm is done when all messages stop. And the initial conditions nodes that attach directly to R. I'm doing a lot of writing today. Nodes that attach directly to R use the distance of that edge and send an initial message. Other nodes set distance to infinity. Okay, so that's the whole algorithm. It's the kind of thing where you really need to see example to understand it. It's much easier through an example than trying to figure out the explanation without the example. Boy, I wish I was ambidextrous. Getting too old to write so much. Jeez. Okay, so let's build a graph. So here's our four, 2, 3. Okay, so there's our A, B, C, D, E, F, G. Okay? So over here we're going to have this big table. Here's R. Well, here's the different node states. So we got node A. We'll even have R run this thing. So R, A, B, C, D, E, F, G. Okay, so initially, remember every node is going to keep track of. Each column is what that specific node knows about. Gesundheit. Okay? So this is not some table that I'm maintaining. I'm showing you every node is individually maintaining this table locally. All right? So initially, R knows its distance to itself is 0 and goes through itself, I guess, to get there. Okay? A's distance to R is initially 1, and it'll go through node R to get there in distance 1. B's initial distance is infinite. It doesn't have a direct connection to R. C's infinite. D's is infinite. E's, the initial distance is 4, and it goes directly through R. F's initial distance is infinite. G's initial distance is infinite. Okay, everybody follow how I set up the initial state? Okay, you'll notice that A already has found its shortest path, its true shortest path to R, but E's actual shortest path, just to prevent ambiguity, this make this edge a 6 instead of a 4. Okay, E has a path length 6 to R, but it's not the shortest path. If you'll notice, there's a shorter path going that way. right? It's just not aware of it yet. You'll see over time it's going to learn the path. Okay, so the rules are that initially everybody who has distance that's not infinite broadcasts their distance information to their neighbors. So let's let A do its broadcast first. I mean, it can happen simultaneously, but let's say A's broadcast reaches its neighbors B and R initially. Okay, so A's broadcast reaches B and it reaches R because those are its two neighbors. So as a result, these two nodes are going to change their state. Maybe. Okay, R checks. A is distance 1 away from me, and it's reporting a distance 1 to R. So if I would get to R through A, it would be a distance 2, which is bigger than 0. So this guy doesn't change. Right? B, on the other hand, now A is reporting to it a distance of 1 to get to R. And B has a distance of 1 to get to A. So if B goes through A to get to R, it has a distance of 2. It can reach R in distance 2 by going through A. Okay? And we said also E reported a distance. So now let's say E's reports reach G and D and R. It's 3 neighbors. Okay, again, R's not going to get any closer than 0, so it's not going to change. D, whatever the distance is going to be less than infinity. So E, and the distance from E to E has length 1, so it's going to be distance 7 going through E, right? And G has distance 8 going through E. Okay, now suppose B updated its information. Whenever your information is updated, you have to let your neighbors know. So B's neighbors are D, C, and A. Okay? A is not going to get any closer. It's not going to change. C, B is claiming to be distance 2 away. C is distance infinity away, so this is going to be closer. So 2 plus 5 is 7. So C is now distance 7 by going through B. And D, by going through B, it's distance 3, which is closer than its current distance of 7. So D switches the path. It's now distance 3, and instead of the next stop being E, it's going to be B. Okay, and G, change when contacted. Now who goes next? I mean, we pick the order arbitrarily. Let's just go with D because this will cause it to converge faster. I'm running out of space and time. But it doesn't really matter which order you choose in. So you know, always somebody whose information was updated. I mean, D is no longer going to send out this information. It may have been sent out earlier, but now suppose D for some reason waited and its information got updated before it got sent out. Then D would always send out its most recent information, right? So whoever can transmit next, C would send this information, D would send this information, or G would send this information. So let's say D sends information next. So D has contact B, C, F, and E. B, C, E, and F. Okay, and B's already closer. It's not going to get any closer by going through D. C's distance is 7. If it goes through D, its distance is going to be 5. So it will change. Okay. E's distance is currently 6. If it goes through D, that drops down to 4. And F's distance is currently an infinite, so if it goes through D, its distance drops to 6. Okay? And you can imagine we continue this process. Let's see. So C would send out a broadcast at this point to its neighbors B and D. Okay, neither of those guys are going to change. E would send out its distance to R, D, and G. And only G would result in changing, right? D is currently 8. If it goes through E, it's now 6. And I think we're done. I mean, then the F would broadcast to, who hasn't broadcast yet? F hasn't broadcast, and G hasn't broadcast. So F would broadcast to G and D. Doesn't make either of those guys closer. And G would broadcast to E, F. Doesn't make any of those guys closer. So nobody else's distances got updated. Nobody else sends any messages. So the messages stop. And if you look at what you got, sort of the last changes that the nodes made, their current tables. Okay, G is going to take the path through E. F is going to take the path through D. E is going to take the path through D. D is going to take the path through B. C is going to take the path through D. B is going to take the path through A. And A takes the path through R. So there's your shortest path tree. And you notice the distances are all correct. Right? A is distance 1, B is distance 2, D is distance 3, C is distance 5. Question? Yeah, Gary.
In the last column, the G column,
Uh-huh.
E.
Yep.
Why don't you check its neighbors after E?
What you mean? Why didn't this guy send a broadcast? It could have, but so you could have had it broadcast to its neighbors, and so the way I presented this, one guy is sending messages at a time, right? That was just for ease of presentation. Could in fact be that they're all sending at the same time, and I just chose the order such that. I picked the order such that this one didn't happen to go next, and before it got a chance to go, it had already updated it again. But yeah, it should have sent something out here, and so there is this change in parallel, and the algorithm still works; it'll still converge correctly, even if all these changes take place in parallel. Every node always has to choose the minimum path distance that it's seen, and go with that. Okay. Let's see. All right, we didn't do split horizon. Okay, I'll give you an extra 2 days to do the homework. So homework's due Wednesday now instead of Monday, because we didn't really get into enough detail on split horizon. We should be able to do the first 3 questions anyway. Almost. So I'm gonna make one slide extension to Bellman-Ford today. That will allow you to do all the homework except the last one. Homework day moved to, what's today? 10th, 17th. All right. So the way I presented Bellman-Ford there, we computed the shortest path tree distance to a single route. Okay. Now what we're going to do is we're going to do Bellman-Ford shortest paths distance to all nodes. Okay, so before, here every node maintained distance to just a single node. Right? The node was the root. Now we're going to do it for all nodes. We're going to look at each node. I'm not going to try and draw a table like that has the information of all nodes. Each node maintains a, let's see, n by, let's say nu sub I table, or n minus 1, well, let's say n by nu sub I table, where n is the number of nodes in the network, or graph, and mu sub I is node I's number of neighbors. Okay, so for instance, node D. D in previous example. Okay, its table is going to look like this. It's going to have an entry for every other node in the graph, including itself. Okay, this last one is R. Okay, and then a column for every neighbor. So these neighbors are B, C, E, and F. Okay? And the entry, so let me just rewrite it in general. This way. Well, neighbors V1 up to V sub k, and all nodes are going to be N1 up to N, let's use L. So just switching notation, k is the number of neighbors. For this node, and L is the total number of nodes in the graph. And let's talk about this entry here. Let's call this entry I comma j. The I comma jth entry in the table, right? Row I, column j. Entry ij holds the shortest, holds the distance reported by neighbor Vj, okay, to node Ni plus W A Vj. This is the table for node A. Node A's table. Okay, so there's some node A that's maintaining this table. And the entry in the ith row and jth column is basically, if I took this path that neighbor V sub I was reporting, or V sub j was reporting, if I took this path that node V sub j was reporting, my distance node Ni would be this distance. People follow that? It's what we were doing over here for node R, right? When node B reported a distance of 2 and sent that report to node C stored 7. Why did it store 7? Because node B was reporting a distance of 2 and node C's distance to B was 5. So it reported the value that's stored is you know, the distance from you to your neighbor plus whatever your neighbor claims is its distance to the destination. Okay? And now the rule is every time a report is received from a neighbor, v sub I, v sub j, which equals alpha 1, alpha 2, not that, alpha L. Okay, so this is node neighbor Vj reporting distances its shortest known distances. To all other nodes. Okay, you add W of A Vj in each entry store values in the corresponding column. Okay, and then for each row, choose the entry that minimizes distance for each row I. Choose the entry that choose the entry that minimizes the distance to n sub I. If different than before, if minimum distance changes. Send minimum distance vector. To all neighbors. Okay, so before we go, let me just give you a quick example. Okay, so let's say I'm node A, my neighbors are C and D and E, and all the nodes in the network are A, B, C, D, E, F. Okay, I don't care about the top row. Let's just ignore it for a minute because what do I care about the distance to myself? I don't need to worry about that. But let's just fill in these columns, or these values. Okay, so these are the columns, these are the values that I have. What this means is that if I go, from what I know currently, if I go through node D to get to node B, okay, I'm going to have to travel a distance 4. And that's less than if I were to from what I currently know, if I were to go through E or C. So I'll choose this entry, this entry, this entry, this entry, and this entry. Okay? So my minimum path lengths, if I were to send out a vector, I would send my distance to A, my distance to myself is 0, my distance to B is 4, my distance to C is 2, D is 2, E is 3, F 6. This is what I would send to my neighbors. Okay, now when I get a vector from one of my neighbors, suppose E sends me a vector. Suppose E sends me 2, 2, 2, 2, 4, 4. And suppose my distance to E, so I'm A. So suppose the weight of edge A to E is 1. Okay? When I get this information, I have to update this column to all these values plus 1. Right? So I would update this column to be 3. Well, this value I don't care about. I would ignore that. 3, 3, 3, 3, 3, 3, 5, 5. Right? In which case, some of my shortest paths would change. This would no longer be circled. Now I would have circled this instead. And this would no longer be, sorry, that one stays. This would no longer be circled. Now I would circle this instead. Right? So my minimum distance has changed. So I would have to create a new vector. Instead of sending this one, I would have to send out a vector 0, 3, 3, 3, 5, 5. No, sorry. 0, 3, 2, 2, 3, 5. 0, 3, 2, 0, 3, 2, 2, 3. 0, 3, 2, 2, 3, 5. That'd be my new vector, and I would send that one out. Okay, so anytime I receive an update from a neighbor and it changes my minimum distance vector, I send that to my neighbors, my new vector. And every time I receive something from my neighbors, I have to update mine. It's the same thing we're doing here. Just instead of just for R, it's for all of them. And instead of just always looking at the minimum current value, sometimes it might grow, and you have to always do the most appropriate update. So we'll pick up on this again next time. But I suggest you try the homework. There's no better way to learn to understand this than by doing it. But we'll pick it up on Monday as well.